Everybody, this is another meeting where the modeling sub-team and the atmospheric collaboration team have gotten together, and we have a list of good speakers. We're focusing on PAMIP, which is the Polar Amplification Model Intercomparison activity. From the modeling standpoint, we have been focusing on MIPS for now 2 or 3 sessions, and that's partly because with CMIP-6 approaching, there are a lot of modeling groups that are working on model intercomparison activities so that their results can be compared with each other, and that way it informs the science. So in the past, we had, from the modeling team, we've had activities that focused on the sea ice MIP, the ISMIP or the ice sheet MIP, and now the polar amplification MIP. And for that, we have, to talk about PAMIP, we have 3 speakers who are very engrossed and work very much with the activities of PAMIP. To start off, we'll have Doug Smith from Met Office. He, along with James Crean and Cara Dessa, are the chairs of the PAMIP group. Doug Smith will provide a general introduction to the PAMIP and motivate the activities. Then you have Yannick Peings from UC Irvine, and he will talk about the work that he is doing with PAMIP and talk about it from the atmospheric point of view a little bit more. And then we have Stephanie Hay, who is a graduate student at the University of Toronto, and she will talk about coupled model activities for PAMIP. So that's a general introduction, and would like to welcome everybody. And what we could do is at the end of each one of the presentations, take a few minutes to discuss ask clarifying questions, and I'm hoping Doug Smith can stay to the very end, and so then we can have a whole discussion at the end. So with that, I invite Doug Smith to kick off the meeting.
Okay, hello everybody, thank you very much. I'll just share my screen now then. Okay, I'm hoping you can all see the first slide.
Yes, it looks good.
Okay, great. So I'm going to give a very brief overview and motivation for the polar amplification MIP. So the objective is to investigate the causes and consequences of polar amplification. We're talking about both hemispheres here, so Arctic and Antarctic. I'm really going to focus on the consequences of Arctic amplification. Really, I think that's what we're probably, most of us are most interested in this meeting. So I'm just going to focus on that. Okay, so the first point I wanted to make was that we cannot diagnose a real-world response to sea ice changes just using observations alone. And I wanted to illustrate that with this figure here. So on the left we have regression analysis of observations. So it's the regression between autumn, so September, October, November, Arctic sea ice, and the following winter sea level pressure with the sign reversed. And this has been used many times to try to diagnose the potential response to melting Arctic sea ice. And what you would perhaps conclude from this is that we see this high pressure over the Arctic surrounded by almost a ring of low pressure. So it's like a negative Arctic oscillation or North Atlantic oscillation response, or pattern at least, and people have argued that this is a response to the melting sea ice. Now, if we perform atmospheric model simulations, these AMIP simulations, and these are an atmospheric model forced by observed sea surface temperatures and sea ice concentration changes over the period since 1979, and then we do the same regression analysis on those atmospheric model experiments, then we get a very similar pattern, okay? So maybe that would support this observed finding. But then if we do specific experiments using the same atmospheric model that's been used for these AMIP experiments, but what we do is we actually change the sea ice pattern in that model and force it with a reduced sea ice extent, then we get the map on the right, which shows a very different pattern. Okay, so in this model, although it simulates the observed regression between sea ice and sea level pressure, when we actually force it with experiments designed to work out the response to sea ice, we get a very different pattern. So the conclusion is that at least in these experiments, probably this pattern is being forced by sea surface temperature rather than the sea ice. Okay, so the real point was that we need to additional information from observations alone if we're going to work out what the response is to changing sea ice. So there have been very many studies trying to work out the response to the melting Arctic ice pack, and I'm going to focus on the North Atlantic Oscillation, the NAO, and basically there is no consensus at the moment really in those studies. So the full range of responses has been reported, ranging from a negative North Atlantic Oscillation with high pressure over the Arctic to a positive North Atlantic Oscillation with low pressure, to virtually no response in the NAO, and to a response in the NAO that depends on the kind of forcing that's been applied. Okay, so there's no consensus at the moment. And potential reasons for that could be that the response depends on the model that's used to isolate it. So this is an example from a paper by Sun et al., where they put the same changes in Arctic sea ice under two different models, and they get a very different response. And especially in the stratosphere, you can see either a weakening or a strengthening indeed of the polar vortex there. So it could just be the model, but also people have found that the response can depend on the pattern of the sea ice forcing that's applied to work it out. So on the left is the model response. So it's a function of height on the y-axis and latitude, and this is the zonal wind response. So on the left, this is the response to Atlantic changes, or reduction of sea ice in the Atlantic, and we see a weakening of the zonal winds in this model. But when the sea ice forcing is only applied in the Pacific sector, then we see the opposite response with a strengthening of the polar vortex. So the response to sea ice seems to depend on the exact pattern of the forcing that you give it. It can also depend on whether we're using an atmosphere-only model or a coupled model. So on the top, we have some results from Cara, and they've applied the same sort of changes in sea ice in an atmosphere-only model on the left and a fully coupled model on the right. And you can see that the pattern is very similar in the two cases, but the response seems to be magnitude when they used a coupled model. Okay, for this. And then on the bottom, we have results of our own study, where now on the left, we have the atmosphere-only model, and on the right, we have a fully coupled model. And now the response is completely different. It's only in the coupled model where we're seeing this weakening of the zonal wind. Okay. The response can also depend on exactly how the forcing is applied. So there are several different ways that we can change the Arctic sea ice pack to simulate future changes. So we can apply a long wave flux to melt the sea ice. So that's what happened in the top left panel there. We can change the albedo of the ice to melt it with a kind of a short wave flux, if you like, and that was the right-hand panel, top right. And in these two sets of experiments, actually they seem to give a very similar response in terms of sea level pressure. And these use the same model, but different ways of changing the Arctic ice pack. But I just wanted to note that on the bottom here, we have a cross-section of temperature with latitude. And in the left-hand panel was where the sea ice changes were imposed using the long wave flux forcing. And in the right hand was a different model, but also a different way of forcing the sea ice by nudging to a different ice concentration. And in the left-hand plot, we see this kind of mini global warming response with with warming in the tropics, in the upper troposphere in the tropics, and that doesn't appear in this other experiment where the sea ice was forced in a different way. So just to highlight different reasons for different responses. And then we also found an interesting dependence on the background state, or the model bias, if you like. So this is from our own simulations with our model, and we're putting in a reduced Arctic sea ice, and we're looking at sea level pressure response. So in the left-hand panel, this is where we had an atmosphere-only model, and we can see a low pressure over the reduced sea ice. So this is basically a heat low response. So we get rid of the sea ice, and we get a warming surface and a low pressure over that warmer surface. And then in the couple, when we run this with the coupled model, fully coupled model, we got the opposite. So a kind of a negative NAO pattern with a high pressure over the Arctic. And we went further to try to understand why this was. And it could be that the coupling is important, or it could be that the background state is important. The coupled model has different biases to the atmosphere-only model. So what we did was we reran the atmosphere-only model, but we imposed the coupled model biases. And then we get the plot on the right-hand side, which basically recovers the same pattern that we got from the coupled model. So suggesting that the key difference here or the key control here is the coupled model bias, or the background state. Okay. And now I just wanted to highlight a very important discovery that's happened recently. It's come from seasonal forecasting, and we've called it the signal to noise paradox. And I'm trying to walk you through this. So on the top left-hand panel, we have an observed time series of the North Atlantic oscillation, the NAO index, in black, and we have the ensemble mean of seasonal forecasts. So these forecasts start in November, and they're for the kind of winter season, DJF. And you can see there's a pretty good correlation between the ensemble mean forecast and the observations. The correlation is around about 0.6. But if you notice, the y-axis here is a normalized one. So we're plotting a standardized time series. If we plot the raw data, which you see on the top right, you get a very different situation. Now you can see the ensemble mean has very low variability, and the ensemble members, which are the circles, have a huge spread. And you could pick any sign of the NAO in any winter that you wanted. And if you just looked at this right-hand plot, you would conclude that there's no real signal in the forecast, okay? But we can see the left-hand one that there is. And what it comes down to is the amount of signal compared to the amount of noise. The signal-to-noise ratio is way too small in the model simulations to kind of be consistent with this amount of forecast skill that we get. So we can illustrate that with the bottom right. So we can actually plot the skill of the ensemble mean, so this red line, versus the number of ensemble members that have gone into making that ensemble mean. And you can see this black line here, the skill actually climbs quite slowly, but reaches this kind of 0.6 level when we have 40 members or more. Okay. Now, if everything in the models was perfectly accurate, then if we swapped one of the model if we swapped the observations for one of the model members, we would expect the model to be able to predict itself as well as it can predict the real world. But actually, we find that the model predicting itself is much lower, has much lower skill. That's this green line here. So paradoxically, the models can predict the real world much better than they can predict themselves. And all this is just a consequence of the fact that the signal to noise ratio is too small in the model simulations. So what that means is that to get the signal, we need a very large ensemble to get rid of the noise and extract the actual signal. So in these PAMIP experiments, they're designed to have a large ensemble. It also means we can't trust the magnitude of the response that's simulated by the model simulations. It could well be too weak, okay? So we can't just diagnose a real world response by looking at the model simulations. We have to be a bit cleverer about that. So one way to do that is to use this kind of emergent constraint idea. So I've already talked about 3 sets of simulations that we performed, one with the atmosphere only model, one with the coupled model, and then one with the atmosphere again, but with a coupled model biases. And we can correlate across those 3 sets of simulations. Okay, there's only 3 points, so it might not be that robust, but we can do something along these lines. And if we do, we find that potentially the differences in these 3 sets of simulations in terms of the response in the Atlantic jet could be explained by the refractive index of the background flow. So basically, there's a change in the planetary wave activity that gets refracted by the background flow, and the amount of refraction seems to explain the different responses we get in our model. Of course, 3 points is nowhere near enough to do this robustly, and that's why we need the coordinated multi-model experiments from the PAMIP. And we also need to understand the underlying physical mechanism so that we can obtain this kind of physical thing that might explain the reason for the differences. In this case, it appears to be the refractive index, but it remains to be seen whether that will hold out when we have more experiments. Okay, so just to summarize, I hope I've convinced you that we can't diagnose the real-world response from regression analysis of the observations alone. At the present day, in the literature, there's a full range of NAO responses have been reported. There are several reasons for this: the magnitude of the forcing, how it's applied, the pattern of the forcing, the background state. So really, we need a coordinated set of model experiments, and this is the kind of motivation for the PAMIP. In terms of diagnosing or assessing the PAMIP experiments, we know that the signal-to-noise ratio may be too small in these model experiments, so we need a large ensemble to extract the signal. We can't trust the model response because it could be too weak, so we need to probably exploit some sort of emergent constraint idea to get a handle on the real world response. And to do that, we really need to focus on understanding the physical mechanism. So just a very brief overview of the actual experiments themselves. We have the first set is atmosphere-only experiments. All of the tier 1 experiments that the groups have to do to partake in this MIP are included in this first set of atmosphere-only experiments. The idea is to run the atmosphere model with present-day SST and present-day sea ice concentrations as a control experiment, and then we will perturb the sea ice concentration. So, for example, we're put in a future sea ice concentration and then work out the response from that. And then we have a set of coupled model experiments, and these are just a year long. So coupled model experiments to repeat that and understand if there's an inference from coupling on that. And then we have a set of experiments. These number 3 is to assess the response to different patterns of forcing. So we're going to put in the sea ice changes only in the Cara, Barents Sea and only in the Sea of Okhotsk separately. And then we have a set of experiments to assess the dependence on the background state, as I talked about earlier. We have a set of experiments to focus on the recent period, 1979 to 2014. And then we have some long coupled simulations that Stephanie will talk about, I think, to try to assess the transient response and the full response in the ocean. So I'll leave it there, and I'm not sure if we've got any time left for questions, but thank you very much.
I knew you're on mute. You need to unmute.
Thank you. Thank you. Doug, you'd be able to stay till the end of for the whole session, right?
Yes.
Okay, so he's calling in from the UK, so it's 8 p.m. for him. So in which case we can have some clarifying questions for Doug if we have any. And then in the meantime, Yannick Peings could start his presentation, load his presentation. So open the floor for questions for Doug.
So can I ask a question? So Doug, what is the timeline of PAMIP in terms of modeling centers contributing their simulations, in terms of analysis and papers coming out of it? Can you comment on that?
Yes. So some modeling centers have started doing the experiments now. So I know of 4 groups that have completed some of the tier 1 experiments. We have a meeting in June, and I'm hoping that there'll be a few more groups will have completed them by then. So I think we would be aiming to submit at least 1 paper, possibly more, in time for the AR6 deadline by the end of the year. And then I think the rest of the groups will continue over the next year or 2.
Mm-hmm. Okay, great. Thanks.
So, Yannick, thanks, Doug. We'll stay till the end for more questions, but now Yannick can talk. We'll be talking about. All of you can read it. So, Yannick, take it away.
Good morning, everybody. I'm going to present some initial results we got from atmosphere-only PAMIP experiments. So that's the list of PAMIP experiments that Doug already presented. So I'm not gonna spend time on this. So we have started to run some of the atmosphere-only experiments that look at the response to past, future Arctic, Antarctic sea ice anomalies. So in this presentation, I'm gonna present only the results for the future Arctic sea ice loss experiments. The experiments consist of 100 members of 1 year long runs. So they are part of the tier 1 simulations of PAMIP. The model we have used so far is a WACAM model from NCAR in the specified chemistry version, meaning that we prescribe the chemistry in the model. The chemistry is not interactive. That allows for lower computational cost, but still keeps a good climatology in the model. The model is a high top model. It has a well-resolved stratosphere. It has 66 vertical levels and an horizontal resolution of about 2 degrees. And it has a prescribed quasi-biennial oscillation, or QBO. I mentioned that because I discuss that later in the presentation. So on the left, I show the sea ice extent in the control run of PAMIP. So that's the present day sea ice simulation, first with a present day SSTN sea ice from observations. And then in the middle, this is sea ice anomalies in the pre-industrial Arctic sea ice experiment. So we see we have a larger sea ice extent in the simulation. And then on the right is a simulation I will describe in this presentation as the future sea ice loss experiment, future Arctic sea ice loss experiment. So that corresponds to a +2 degree global warming sea ice extent based on projections from semi-5 models. So we see that we have a large decrease in sea ice in all Arctic in this simulation. Then here I show the annual cycle of Arctic sea ice extent in the 3 simulations. So in orange, that's the present day, the control simulation. So we see the maximum of sea ice in winter, then the minimum of sea ice in fall. And in our future Arctic sea ice loss simulation, so that's in red here, we see that we decrease the sea ice extent throughout the year, and especially during fall. So the sea ice loss is most pronounced during the minimum of sea ice. When the sea ice, the Arctic is almost ice-free in September. So that's the forcing we impose in our model. And we are looking at the atmospheric response to this forcing by looking at the ensemble mean of our simulation, the average of the 100 members. So here I show the thermal response to the forcing. So of course, because of the sea ice loss, we simulate a strong warming over the Arctic that extends a little bit over the high latitude continents. So this is in fall, that's the average between September and November. And then on the right, I show the response of the turbulent heat flux, the sum of sensible and latent heat flux. And that's in winter. Because although the sea ice loss is most pronounced in fall, the response in heat flux is stronger in winter. And that's because that's the season when the air sea temperature gradient is maximum and when the sea ice anomalies will have the largest impact in terms of heat flux. So we find that over the areas of decreased sea ice, there are positive heat flux anomalies, meaning a release of heat from the ocean into the atmosphere. So then I show here a cross-section of the zonal mean temperature response. So on the horizontal axis is the latitude. On the right, we are at the pole. On the vertical axis are the pressure levels from the surface to the tropopause. And we see that we simulate a strong warming at the surface, but actually the warming is quite confined near the surface. doesn't propagate above 850, 700 hectopascal. So then I present the response of the atmospheric circulation in winter, looking at the zonal mean, zonal wind, again as a cross-section, so it's an average across all longitudes. And I show the response in winter for WACAM on the left, and I also show the response for two other models for which we have also preliminary results, the UK Met Office model, and on the right, that's the Alfred Wegener Institute model from Germany. So in green on those plots, it's the climatology of the zonal mean, zonal wind for each model. So we see the subtropical jet. In the mid-latitudes, we have the westerlies, or the so-called eddy-driven jet. And in the polar stratosphere, strong westerlies of the polar vortex. And in color is the response to the future Arctic sea ice loss forcing. And there is quite a consistent response in the troposphere in the three models. So we find weakening of the westerlies on the poleward flank of the eddy-driven jet in the three models. However, if we look at the stratosphere, it's much more contrasted. So we have a weakening of the polar vortex in WACAM, a little bit of weakening in the Met Office model, but more of a strengthening in the Alfred Wegener model. But actually, if we look at the Alfred Wegener model, it doesn't seem to have a very realistic representation of the polar vortex. But it's very important, this stratospheric response, because we know that in winter, there is a strong coupling between the stratosphere and the troposphere. So the stratospheric response can really have an impact on the tropospheric response. Then on this plot, I show a geographical repartition of the response, looking at the zonal mean, the zonal wind again, but at 200 hectopascal. So we see this ring of negative zonal wind anomalies that reflects a decrease of the westerlies in the mid-latitudes, especially over the North Atlantic. So here we see the eddy-driven jet over the North Atlantic, and we see a dipole of zonal wind anomalies, meaning there is an equatorward shift of the eddy-driven jet in winter. This signal is actually more pronounced in the Met Office model that has a stronger response, but it's also consistent in the Alfred Wegener model. So the three models, they agree on the tropospheric response and on this equatorward shift of the eddy-driven jet stream. But as I mentioned, there is less agreement on the response of the polar stratosphere. Now I want to focus on WACAM and discuss the signal-to-noise ratio, and that are actually linked to what Doug discussed and the signal-to-noise paradox. So what I show here is the same zonal mean, zonal wind response in WACAM for the 100 members that I've shown before, except that here I only show anomalies that are significant at the 95% confidence level, just using a simple student t-test. And we see that just using this statistical test, there is quite a lot of anomalies that are gone here, and the only significant anomalies are those negative anomalies in mid-latitudes. But then we have extended our ensemble of simulation to check the robustness of the response to 300 members. And then we can look at the response in members 101 to 200 and members 201 to 300. And what's a bit worrisome is that actually the response is gone in the two other chunks of experiment, and we do not find this weakening of the westerlies and mid-latitude in those two experiments. If we look at 200 hectopascal, we see those weaker westerlies in our first 100 members, but then again, if we look at the two other ensemble, this signal is pretty much gone. So it means that there is a large influence of internal variability in the simulation, and still with 100 members, we can feel the effect of internal variability. So that may be related to the signal-to-noise paradox and the fact that the model, they are too insensitive to the forcing, and the amplitude of the response is too small. Then to discuss also the effect of the model mean state on the response, I just show here the effect of having the QBO or not in our simulations. So we are in our initial simulations, we had the QBO that is prescribed in WACAM because the model, as most atmospheric models, does not spontaneously simulate a QBO. So what we do in our simulation, we prescribe the QBO, so that is this cycle, this oscillation between easterlies and westerlies in the equatorial stratosphere with about 28-month cycle. So we impose this signal, this cycle in WACAM by nudging the zonal wind in the equatorial stratosphere. But then we have reproduced our simulations in a version of WACAM that does not have the QBO, so we do not impose this nudging of the QBO in the model. So we see on the lower plot that we don't have the QBO anymore in this simulation. And then if we reproduce our present day Arctic sea ice simulation and the future sea ice loss simulation and look at the response, we find that the response is quite different when we don't have the QBO. And it's actually quite robust in this case. We find a strengthening of the polar vortex when we don't have the QBO, and it seems to be due to the fact that having the QBO in the model reinforces the strength of the polar vortex, so it changes the sensitivity of the polar vortex to the forcing. So when we don't have the QBO, the polar vortex is weaker in average and tends to reinforce in response to the sea ice loss forcing. So that's an illustration of the effect of model mean state on the response and the need to have large ensemble of models to apply an emergent constraint approach to understand which climate parameters, parametrization, or model mean state parameters are really important and have an influence on the response to sea ice loss. So as quick conclusion and future research, so we show that initial experiments with prescribed future Arctic sea ice loss are quite consistent in the tropospheric response with an equatorward shift of the eddy-driven jet. That is, by the way, opposite to the projected influence of anthropogenic forcing. That's a so-called tug-of-war between the effect of Arctic sea ice loss and the general response to climate change. We find that the response of the polar stratosphere is non-robust in these experiments, which may increase uncertainty in the tropospheric response due to the importance of stratosphere-troposphere coupling. In our WACAM runs, we have a strong influence of internal variability still present in 100 years of simulation. And we also find that the response is affected by the representation of the QBO. So that's something we'll discuss to the PAMIP workshop, because I think it's important to share those results with the community. We have additional experiments with different forcing that we're analyzing now. Also, we'll have additional simulation in which we'll also include sea ice thickness anomalies, because in those simulations, we only modify the sea ice extent. So that may increase the atmospheric response. And also, of course, we'll have the coupled simulations, ocean atmosphere simulations, coupled simulations, in which we expect to have a larger response too, based on the previous literature. And we are running similar experiments with the energy exascale Earth system model, E3SM, from the Department of Energy. And yeah, we are looking forward for those new simulation and simulation from other models from the PAMIP ensemble. And that's it. Thank you.
Thank you, Yannick. Any clarifying questions for Yannick as Stephanie Haylog pulls up her presentation?
This is Hailong from Pyongyang. I just have a very quick clarification question. So when you perturb sea ice concentrations, do you also have the perturbation to SST?
Yes,
prescribed to?
I forgot to mention that, but where the sea ice is decreased, we also apply the SST anomalies. So we have warmer SSTs in the areas of sea ice loss.
Okay, yeah. Thanks.
Yes.
And for all those 100 ensemble members, are they systematically perturbed, or in the same way for different models, or just depend on each individual model?
They differ by their initial conditions. So there is a small perturbation applied to their temperature to create an ensemble of simulations.
Okay, thank you.
So it's Doug here. I've got a question, Yannick.
Yeah.
So for your QBO experiment, so you showed that with 100 members, the stratosphere wasn't robust. Stratosphere response wasn't robust. So how many members do you have for those QBO experiments now?
So you mean looking at the difference between simulation with and without the QBO?
Yes.
Yeah, so we have only 100 years for the simulation without the QBO. So it may be non-robust, you're right.
Okay.
So yeah, I'm extending also the simulations to 300 years.
Right.
To make sure this QBO signal is really robust.
Okay, thanks.
And just to follow up on Hailong's question, so these are with prescribed sea surface temperatures, right? These simulations. But
Yes.
What is being done? How is the sea ice being treated? Is it also like just a fixed surface temperature in a fixed albedo, or how is the sea ice then interacting with the atmosphere?
So the sea ice is simply prescribed. The albedo is fixed, I guess, yeah, depending on the model, but yeah, it's just the same interaction with the atmosphere, except that the sea ice is prescribed.
Right, but there's still like a heat flux coming out of the sea ice, for instance, like there is out of the ocean?
Yeah. All the exchanges with the atmosphere are still there.
Mm-hmm. Okay.
Yes.
Thanks.
So Yannick, can you stop or stop the presentation mode so that Stephanie can bring up her slides, and as she's bringing up her slides, we can have a few more questions. Any more questions for Yannick? So this is just a clarification question. Maybe I missed it. I just didn't understand the difference between the 100, 200, and 300 members. How you just increase the member of the ensemble, and or were there different simulations, different perturbations that you did to get the results you did?
It's the same simulation with exactly the same forcing. We just increase the ensemble size. So instead of having 100 members, we have 300 members, but the forcing is exactly the same. And then we find that the response doesn't hold from one chunk of simulation to the other. So meaning that the response does not seem to be very robust.
So if you would do the analysis on a full 300 member ensemble, would you find any significant responses?
Yeah, it's very small. I mean, it's only in the stratosphere, it's non-robust for sure. In the troposphere, it's a small weakening of the westerlies, but it's not very robust. Yeah, no, it's pretty small amplitude. So that's for this atmosphere-only experiment. So maybe in the coupled simulations, it will be different. We'll have a larger response. Yeah.
Hi, this is Gudrun here. I just have a comment on the forcing. So this is the PAMIP forcing. We've run similar experiments where we allow the sea ice to get thinner as well as decrease in area. And we get a much more robust response. Yeah. So sea ice thickness is important. Also, this is for 2 degrees warming. So it's kind of mid-century or just after the middle of the century. It's pretty weak forcing compared to other simulations that have been done.
Okay, thank you. And now Stephanie Hay from Toronto is going to be doing talking more about coupled model simulations for PAMIP. So Stephanie, take it away.
Hi, everyone can hear me? Yeah?
Yes.
Yeah, okay, great. Okay, so I'm presenting this part of the discussion on the coupled model simulations on behalf of Paul Kirshner today. He's flying back to Europe. Some of the key points of this presentation are sea ice loss. The sea ice loss experiments will provide key insights into polar amplification. While sea ice loss itself is not the only cause of polar amplification, it is a part of it, so it does provide some insight. We have found in our simulations that we're looking at different models and across different forcing methodologies, we actually find that the atmospheric response, in the near surface atmospheric response, is relatively robust, and particularly when you compare it to the response to isolated low latitude warming. On the other hand, the ocean response in these models is really not robust at all. And so we have some recommendations for how to look at this in PAMIP. All right, so showing these figures here from Clara Desser's 2015 paper comparing prescribed sea ice and sea ice loss in an atmosphere-only model on the top here for CAM4, the response you get in zonal mean temperature and zonal mean wind, compared to including a fully dynamical ocean component in your model and reducing sea ice. So you see that the amplitude and extent of the response to Arctic sea ice loss in both these variables is increased. It's about twice as large, and you end up getting a much stronger response in the southern hemisphere as well, even though the forcings only applied in the northern hemisphere. And they say it drives this mini global warming response. And you can see it as well in sea level pressure on the right-hand side. You get the same pattern of response, but when you include the dynamical ocean, it's increased somewhat in extent, and the response itself is stronger. James Green looked at a number of different models where sea ice, number of different coupled models where sea ice was reduced in different methods, by different methods, and he finds that when you scale by the amount of ice loss in the model, and that's the number in the bottom right-hand corner, we find actually that there's quite a robust response, particularly not so much in the stratosphere or in the tropics, but in the high latitude, troposphere, and mid-latitudes. The mechanism by which this occurs is it's actually quite rapid. So it's there's this paper that came out last year by Wang et al. And they compared ice loss in a coupled and a slab ocean model, and they found quite quickly the there's a difference in the response in this SSTs, and they draw attention to this warming feature that occurs. It starts to occur about 40 years in, I believe, and they find that this warming feature in the tropical Pacific is a key component of getting these types of responses in all the coupled models. So some of the work we've done here, so this is looking at the zonal mean temperature in the large ensemble, the CSM large ensemble, so the projected greenhouse warming at, I think this is by about 2060, compared to the simulations that we ran here with CSM, where we used albedo forcing while keeping radiative forcing constant at year 2000 levels. We write it out for many centuries, and we get an equilibrated response, and this is what we find. So like the other models that have already been shown, the warming is not just confined to the lower troposphere and the high latitudes, but it extends further into the mid latitudes and up into the Arctic mid-troposphere. and there is some warming in the mid-troposphere in the Arctic, in the tropics. So this brings up the question, how do we account for what we're seeing in the response? Is it driven by the warming that occurs in low latitudes that it feeds back into the mid latitudes, or is it a direct result of the ice loss? So we use pattern scaling to answer this question. I'll show you the results of pattern scaling before I go into the details of the math. So you decompose the full response into two parts, and you say that one part you can scale with tropical warming in the case of no sea ice loss, and that's what I'm showing here. And then the other side is the part of the full response that you could say is attributable to sea ice loss in isolation. So if you compare B and D, you see that a lot of the warming in the Arctic mid-troposphere is gone now, as is the warming in the tropics. So that was induced through warming of lower latitudes and not directly due to sea ice loss. So, so in a little more detail of what this pattern scaling is, you can apply that method to any internally forced variable. So for example, showing here, the zonal mean wintertime zonal wind response, where these panels are the same as they were on the last slide. So at the top left is the CSM large ensemble response, zonal mean zonal wind, and on the right is the response to ice alone in our simulations. And when you calculate using these equations on the left-hand side, you can then decompose it into two parts. And we get a part that scales with low latitude warming and a part that scales with ice loss. This variable is useful here to show the idea of a tug of war between what lower latitude warming imposes on the atmosphere versus what Arctic warming imposes on the atmosphere, because you can see they kind of cancel out in the full response, but when you decompose it, you get a tug of war. So we then looked at the response of a few variables after decomposing it into a part that scaled with sea ice loss, and we found that the responses were quite robust across the four models we looked at, which were CSM, CAN-ESM, CNRM, and the GFDL model. So I'm showing on the top here the surface temperature, sea level pressure, 850 zonal wind, and precipitation response. This is the mean of the four models after they've been scaled. So we find warming directly over the Arctic that extends over the high latitude continents a bit as well. And you actually find this bit of cooling in Siberia, which has been noticed before. In the sea level pressure response, we find in general a deepening of the Aleutian low and higher pressure over Eurasia. The 850 wind response is in agreement with the sea level pressure response over Pacific here, where you have increasing of these winds here, and then they find this decrease of the 850 winds closer towards the pole. Precip is a bit of a messier variable, but we actually did find some robust features in the response. In particular, with the more open water over the Arctic, we find that there's an increased precipitation directly over it. We also find, in general, decreased precipitation over the North Atlantic, as well as an increase in precipitation along the west coast of North America, although its exact position does vary a bit in the models. And I'm showing here the wintertime response. And to look at how well these patterns agree with each other, we did a pattern correlation between each model and every other model for each variable. And that's what I'm showing on the bottom here by season. So the surface temperature, for example, is right below here. So in wintertime, there's a really high pattern correlation among the four models. Basically, they all agree on the exact pattern of response. But in general, in all the variables, this is not true in summertime, the forcing is weaker due to sea ice loss. So we find quite a varied response in summertime. So we could also then look, because there was the two panels when we scaled things, the scaling with low latitude warming. And I'm just going to show one variable here because I think it demonstrates the message pretty well, and that's sea level pressure. So across the four models, CSM, CAN-ESM, CNRM, and GFDL, we find a varied response that scales with low latitude warming. Really can't, this response itself is not robust, or few aspects of it are robust compared to the robust responses with sea ice loss. And this also brings me to another point, that tug of war between high and low latitudes. So for example, all the models agree that the high latitudes should induce a deepening of the Aleutian low. So CSM would argue that there's a tug of war between what the low latitudes are imposing versus what the ice loss is imposing, whereas CAN-ESM and CNRM actually say the opposite, that they would reinforce each other. So we find that tug of war is actually model dependent. And finally, this is the stuff that I've been looking at most recently, and that's how does the ocean respond in these simulations. So I'm going to show here the response in sea surface salinity after we've scaled the part that scales with sea ice loss. And sure, you can see here there are a few similarities of general freshening of the Arctic Ocean, as you would expect with sea ice loss. And aside from that, there's not all that many things that are actually robust about this at all, despite the fact that the atmosphere's response was quite robust. And in particular, if we zoom in on the North Atlantic, because it's a region that would be sensitive to changes in salinity, you can see that there's not much to say here that's robust. So for, some models are imposing salinification, some are just freshening everywhere, and some have some mixture of the two. And so potentially this can lead to large differences in the way, for example, the meridional overturning circulation would respond in these models. And as it turns out, it does, because if you have a different density profile in the North Atlantic, you're going to have different changes to the regions of convection for the descending branch of the AMOC. So I'm going to show here two models just to demonstrate two that behave quite differently. So CSM, and so the red one is the control simulation. The blue one is our albedo force simulation. And so you can see that the AMOC strength actually decreases just a very small amount due to sea ice loss alone, and then recovers by the end of our simulations to being the same strength. And for comparison, the black here, this is the ensemble, large ensemble. So for the same amount of sea ice loss in the large ensemble, there's quite a larger decrease in the strength of the AMOC. So this model seems to imply that ice loss, so freshening of the North Atlantic, as you might expect due to sea ice loss, is not the main driver of decrease in the strength of the AMOC, but it's the response in total. And then on the other hand, the Canadian model, CAN-ESM, so what I'm showing now is actually a difference in the AMOC index as opposed to the AMOC index itself, because these are all equilibrated simulations. So the difference in the full response to global warming is the black. So overall, it's negative. There's a slight decrease in the strength of the AMOC due to both ice loss and radiative forcing. And the ice simulation itself actually shows a stronger decrease in the strength of the AMOC over time than the full simulation does. So that leaves the CO2 forcing actually to drive an increase in the strength of the AMOC. So a complete opposite behavior to CSM, where the ice was actually a minor impact on the AMOC strength. So yeah, it's offset by a strengthening due to lower latitude warming. So going back to the PAMIP-coupled model simulations that Doug was showing, so the first set of model coupled simulations were these 1-year simulations, which are so 100 members of a 1-year simulation, and we have discussed, we're not sure what that means for a coupled model, in that does the ocean actually have any time to respond in a year to get to make it meaningful to use a coupled model on that type of time scale? And then the other sets of coupled simulations are these longer ones, which are closer to what people have been doing so far, and might be closer to the observed variability due to allowing the ocean a chance to propagate a signal.
Excuse me. Oh.
Was that?
Yes, Stephanie. Mm-hmm.
Yes.
No, I just wanted to say we need to speed up. We've got just 2 minutes left for the whole call, and I was just wondering. Thanks.
That was my last. This is my last slide. Just the recap.
Okay. Great. Thanks a lot, Stephanie. Do you have any questions for this part of the presentation? If so, after that, we can go to a general discussion. If you don't mind, we can extend the meeting for another 5 minutes at least after that. So any questions for Stephanie?
Well, it's Doug here. So I was just wondering, Stephanie, whether you have any recommendations for those long ocean runs, experiments, how to impose the sea ice changes.
So I don't know what the correct way to do it is, but I think based on our results so far in the ocean that there should be a consistent way of applying the forcing, so that we can at least disentangle whether the differences in the response in the ocean are a result of the method itself, or are they implying that actually the ocean response itself is not important to obtaining the atmospheric response.
And this is Hailong again. So I wonder about the snow over land and also over sea ice. How long time do you leave the model for 1 year runs to spin up to get the correct snow cover?
I don't know the answer to that question.
Maybe that for Doug or Yannick.
Sorry, could you just repeat the question?
So I wonder about, because sea ice, SST are all prescribed to the model, but you cannot get snow over land or over sea ice. So how long do you think the model can pick up the correct snow cover?
So I think that the snow would be free to respond to the sea ice changes. And we've seen changes in precipitation already. So I would expect to see something there already in those 1 year runs. And then with the longer 100-year runs, that should be plenty long enough.
Yeah, 100, I agree, 100 years should be enough. But I wonder for 1 year.
Yeah, well, we'll just have to see on that. I mean, there are clear changes in precipitation. Yeah, I don't know the answer to that. We'll have to see what it looks like.
Okay, thank you.
Stephanie, can I ask one question? You may have mentioned it, but the ocean results that you showed, how long were those integrated for?
So it depends on the model itself. They're all at least 100 years.
Okay, so not the 1 year coupled simulations from
No.
the protocol. Okay, thanks.
Well, there are two sets of coupled simulations in the protocol. There's the 1 year ones that parallel the atmosphere only runs, and then there are these 100-year ones, which at the moment the protocol is flexible for that. I mean, it suggested that people use relaxation to impose the sea ice, but it could be done in other ways too. It's kind of left open for groups to experiment at the moment, because we couldn't think of the best way to do that.
Mm-hmm.
I have a question for Stephanie. So some of the published coupled simulations have shown a response in the tropics. Have you looked at whether there is effects on the oceanic circulation in the tropics associated with in these experiments?
We have not yet. No.
This is a very general question. So two people mentioned emergent constraints. What are the kinds of emergent constraints that you are expecting? What are the other constraints that you're expecting? What do you expect to see at the end of this?
Sorry, was that question to me? A general question.
It's a general question. Both Doug and Yannick mentioned it. So.
Yeah, so I see this as a key part of the analysis. So we totally expect the models to simulate different responses to the same forcing, and actually we want them to do that so that we can use this emergent constraint idea to try to find something that we can observe that explains the model spread, essentially. So in the example I gave, the model spread seemed to be explained by changes in the refraction of the planetary wave activity. Now, if that holds up in the multi-model case, that would be great, but it could be something else. But what we need to do is to understand the physical mechanism that causes the model spread, and then relate that to something we can observe, and then we can, from using that approach, we can hopefully work out the magnitude of the real world response, which we can't do from the models alone. One, because they give different responses, and two, because their responses may well be too weak because of this signal to noise paradox.
Can I ask a question as well? This is Vladimir Alexei from the University of Alaska Fairbanks. So when we talk about responses to sea ice and how sea ice changes, we probably should not separate mid-latitude impact from the local feedback. They all interact. So what I think, in order to disentangle the local impacts versus non-local, we probably could think of an experiment where a regional climate model can be utilized with some fixed circulation on the boundaries, so that we can actually look at the impacts of, let's say, warmer Pacific or warmer Atlantic on the circulation in the Arctic and vice versa, how the local circulation will respond to changes in the sea ice. So basically what I'm saying, have you ever thought of designing an experiment with regional climate models to look at local versus non-local impacts in your project? I would be happy to come up with something if you think this is interesting.
If that was to me, then no, we haven't.
No, it's to everyone, to everyone.
Okay. So, well, we didn't think of that when we were designing the PAMIP experiments. We didn't nobody proposed that at all. So if you have something to suggest there, that would be great.
Certainly.
I have a general question. So these are obviously very large experiments, and the CMIP deadline, of course, is very rigid. Are there any plans to systematically evaluate these experiments out after the CMIP deadline? I'll send that to Doug.
Okay. We don't have firm plans at the moment. I think there's certainly will to do some multi-model analysis in time for the CMIP deadline. But beyond that, we don't have any firm plans at the moment. I mean, obviously, these experiments are going to generate an awful lot of interesting data. And the real power of them comes in understanding the model spread, I think. So I certainly think that there's plenty of room for further analysis beyond the end of this year of all these, nice new experiments. But we don't really have a plan to do that at the moment.
Other question, Richard? No. Okay, Doug. You mentioned that this PAMIP was also meant for the Antarctic. Can you comment on that? Is there a similar experimental protocol set up and expected to be executed for Antarctic sea ice? Yes.
So part of the Tier 1 experiments do involve equivalent changes in the Antarctic. So, for example, we will impose future Antarctic sea ice changes, and we also have the pre-industrial simulations with both Antarctic and Arctic sea ice. So there are equivalent experiments to the Arctic ones that are Tier 1 and should enable to assess the impact of Antarctic ice as well. And also part of the PAMIP is to work out the causes of amplification, and in particular the roles of local sea ice changes and remote SST changes in driving the amplification in both poles.
Great, thanks.
Thanks. Any more questions? There are plenty of questions that come to mind. What I'll be doing personally is to be tagging the speakers and asking for responses. So if others want to do it, that would be a good way, because we've already got over by about 9 minutes. So I think for right now, if it's appropriate, Sarah or Meredith, I'm planning to say that we are done with questions for now, and please do send emails or tag the speakers as part of the presentation and ask them questions. So with this, I conclude this particular meeting. What we will be having next month as part of the modeling team collaborations presentations would be something focused on terrestrial ecosystems, and the atmospheric collaboration team would be focusing on Greenland stations. Okay, that's it. Thank you very much. Thank all the speakers too. Thank you very much. It was very useful.
Thank you.
Thanks for calling in, everyone.
Thanks.
Thank you.
Thanks, everybody.
Bye.